64% of developers using WebAssembly or WASM say they're using it to port existing applications to new platforms. My name is Paul Nashawaty, and I'm the practice lead for the app dev practice at theCUBE Research. I'm joined today by Matt Butcher from Fermyon. Matt, how you doing?
Good, thanks for having me. Fermyon's been around now. We're coming up on our third year. I'm the CEO there. We are really looking forward to all the cool things that are happening right now in kind of the serverless and edge landscape. So really excited to talk to you today, Paul.
Yeah, great to have you. It's always great to talk to you. All of our sessions that we've had in the past and everything, watching your journey has been really exciting. So let's jump right in. There's a lot. You mentioned, serverless, and I know that that's a big trend that's happening. Due to the ability to simplify cloud adoption and application management and development, also to reduce infrastructure management, serverless often offers that cloud effectiveness, especially as cloud providers are investing heavily in serverless services and the ecosystem around it. Why do you think serverless is trending again now, Matt?
Yeah, and I think a good place to start with that is to sort of just quickly say, what is serverless and why? Why has it sort of taken off in the past? And then what are the evolutions we're seeing? So serverless, to me, when I talk about it, I think primarily in terms of a design pattern, right? Where application developers are responsible for writing snippets of code that respond to events. So we could contrast that with the kind of server model we've seen around since the 70s, really, where a server stands up and it listens for a long time and it handles hundreds of thousands, even millions of requests. And when a server goes down, it's sort of a failure mode, right? Serverless was really sort of inverting that pattern and saying, no. A serverless function is only going to execute when it's handling a request. So you're using no resources when the serverless function isn't running. A request comes in or an event gets triggered or something happens, that function starts up, does its work, and shuts down. Now, that's serverless in the sense of there is no software server daemon, the way we would talk about it in sort of old school Unix dialect, right? But it's also serverless in the sense that because these workloads are very reactive, they can be moved around very easily. And consequently, we don't have to sort of take this proactive IaaS approach of managing our infrastructure. The kind of canonical serverless platform for the last decade has been Amazon Lambda, right? Originally, Amazon was trying to figure out a way to deal with the spare capacity they had in their compute clusters, and they figured they could carve off little time slices and be able to build this event-based system where I, as a user of AWS, could upload my serverless function, and an event would trigger, and my serverless function would run, handle that event, shut back down again. It is one of Amazon's most popular services now. And in fact, I think they say they handle something like 1 trillion requests a week of serverless functions. I mean, just mind-boggling numbers. These are all, user code. Originally, this platform that was built to make use of spare capacity has now evolved at Amazon into this massive platform to just handle all of the inbound serverless. That was really sort of serverless Gen 1. And you saw, Azure jump in there with Azure Functions. You saw Google jump in there with Google Cloud Functions and Google Cloud Run. And you really started to see sort of this proliferation of people also trying to mimic this same model. But we hit a limit. And the limit started to change the way that we viewed what we could do with serverless, right? You cannot run serverless functions as frontline compute. And the reason why is because there's a cold start problem. What that means is when a request comes in, it takes the platform a little while to stand up all of the code that will then handle it, return a response, and shut back down. In fact, it takes about 200 to 500 milliseconds on Lambda, a little tiny bit longer on Azure Functions. And we hear these numbers and we think, yeah, 200 milliseconds, that seems like a very short period of time, but when you're dealing with performance for frontline web services, it's actually kind of a problem. Google did some research several years ago into basically bounce rates and cart abandonment rates and its relation to performance. And what they discovered is that at 100 milliseconds, which is actually the speed of the blink of an eye. Your eye blinks at about 100 milliseconds up and down. At one blink of an eye, if you are not showing your end users something happening in their web browser, their abandonment rate begins to go up. People stop their e-commerce motion. They get distracted by their phone. They start drifting toward email. Your bounce rate starts to go up at 100 milliseconds. So if it takes 200 to 500 milliseconds to get from the request being received to your customer's code executing and serving those end users, you're already placing your customer at a disadvantage, right? And so we looked at this problem and went, okay, if serverless is going to outgrow its sort of utility computing background, we have to really focus in on this performance story. We have to tell a performance story that is just so much better than what's out there today. And when we started looking into that, we started realizing that, runtime wise, a lot of this was because these things were built on Gen 1 IaaS technologies, right? Again, going back to that AWS origin story for Lambda, it was built on the idea that they could, kind of squeeze a little bit more out of spare compute. It was not built saying, what's the fastest runtime we could have? What we're seeing now in this sort of next gen of serverless is a transition in desire for people to say, no, we really like that developer pattern and we need to be able to run it in a faster kind of runtime so that we can build our frontline services on it. The place where I think that's taking off in a lot of cases is really more in e-commerce, in media, in places where that sort of sensitivity to latency is very, very high. And I think we're starting to see it move a little bit more toward the edge now. And I think we're really starting to see a breakdown from the client server model that's been prevalent since, late 70s, early 80s into this sort of like continuum of compute story where the edge isn't just a cache. The edge is a place where you can do more computing.
Yeah, Matt, this is great. You kind of went into a lot of detail there, and I think that's fantastic because it makes sense to me, makes sense to the audience, I believe, on how this evolved to where we're at today. We're seeing the use of WebAssembly, for example, in our research today. 39% of organizations are using WebAssembly, and that's just growing. You mentioned Edge, and native Edge as a software platform really helps that businesses manage to scale to Edge, the infrastructure and the applications. We're seeing a lot happen at the edge because there's a tremendous amount of growth, right? Where there's hardware and software that are changes, things they're using heritage technologies as well as new technologies, and recompiling applications is just not really the option. Right. And by doing so, like when we talk about this, we're seeing also in our research that 500 to 1,000 net new production workloads happening at the edge locations over the next 2 years, with 54% today using production workloads using AI, right? So there's a lot happening at the edge. You talk about in our conversations, in our briefings, we've talked about edge native. What does edge native mean to you? And like, what does it mean to like how is it distinguished from the cloud native? And like, what's the difference here?
Yeah, you just set the perfect foundation for this discussion, right? We all kind of have heard the term cloud native used a lot, and that was a term that was sort of coined to describe that transition period we were all in moving things from sort of on-prem in-house data centers into the kind of public cloud technologies we would see with AWS and Azure, right? And then even more so as technologies like Kubernetes and containers evolved, we saw, cloud native become sort of synonymous with containerizing your workloads and deploying them through orchestrators like HashiCorp Nomad or through Kubernetes or something similar. Edge native is kind of capturing that next sort of evolution. And again, as we go from sort of a client server sort of model into a continuum of compute story, where there are, compute is sort of spread out all between the end user and the big data centers running on the East Coast and West Coast in the US and in London and places like that. We're starting to see little pops spring up sort of all over the place that were originally built for things like content delivery networks, right? Where it was just a way to speed up static assets. But as compute power has grown there, and as developers have gotten a lot more savvy about how to, cut down network transit time and things like that, we've seen this evolution into what I think is best described as edge native computing. And what that means is applications are no longer living in data centers and being accelerated through edge technologies. Applications are no longer being deployed only in Kubernetes, only in US West 2 or whatever. They're being deployed into the edge. And there are no necessarily upstream data centers in some of these cases. So there's both an augmentation story where the edge is performing more functionality than it used to. It's not just a cache, it's a compute engine. And there's the full-on edge native application story where the application itself runs distributed across the edge. That is sort of a big transition point for how we can deliver content quickly to end users, often more cheaply to end users, and still take advantage of many of these emerging technologies and existing technologies. WebAssembly, I think, plays a really good role in this, because one of the issues with edge technology has been that you would end up on a hardware SKU that maybe was different from what you were running in the cloud. WebAssembly as a technology, if you're just kind of considering at the base, what is WebAssembly? It is a high performance platform architecture operating system neutral binary format that can execute very, very quickly and securely. And with just those little, just those particular attributes, it means it's a great fit to run in a data center. It's a great fit to run inside of your car's computer. It's a great fit to run on this sort of edge, distributed edge platform that you see in sort of the classic CDN sense of the word, right? And that's what is exciting to me, is that WebAssembly engine is turning out to be the really excellent substrate for enabling, edge native application development.
There's no doubt. I mean, our analyst reports are showing, what our research is really showing, that businesses had a mindset at the edge of set it and forget it, and that was a problem, because there's usually a lot of verticals like retail and finance and healthcare or whatever. They don't have really technologists at these edge locations. And there's a lot of problems, but performance, speed, and efficiency is really incredibly important when it comes to these new applications. So, but I think you also touched on something, Matt, that was really, it's intriguing to me, because I just think of heritage environments eventually just being upgraded. And what I found, especially in verticals like manufacturing, or those some specific verticals like maybe even finance as well, that they're leveraging heritage hardware and heritage architectures. So to harmonize that, they're looking for a way to create net new applications and use those net new applications across these different devices. So new devices as well as heritage devices. And think about things like smart cities. Right, smart cities is another area where, that's where I think that the edge and AI are really kind of coming together. I can't help but have a conversation without saying AI, because we all have to, right? But I think that it definitely plays into it when we look at the impacts and the news that is happening. So what are your thoughts around edge and AI, and like maybe bridging the gap between the old and new, and kind of tying it all together?
Yeah, and so Fermyon works with Akamai. We run inside of Akamai's edge, and for sure, everything you just said resonated very much with me, in the sense that when you're dealing, so Akamai is in fact the world's biggest edge network. They have just thousands and thousands of points of presence, thousands and thousands of POPs. You cannot upgrade all of those POPs to giant hardware profiles to be able to run an entire virtual machine or large containers. So you need a runtime that's really going to be very svelte, and is going to be able to run on this kind of heritage infrastructure, but still kind of meet the performance levels that people are expecting out of the most contemporary platforms. That's a very hard target to hit without a technology like WebAssembly. And then, along comes AI. And AI has been fascinating, because I think we're already seeing a very rapid iteration of the way that we think about it. Originally, a year and a half ago, when we talked about AI and we were talking about the hardware profile of the machines we needed to run AI, everybody was saying more GPUs, bigger data center, more GPUs. Let's just pile in the highest powered GPUs we can into the data center. That story does not work well in these kind of heritage environments, right? They are not created to be able to handle 100 H100 NVIDIA GPUs all racked in the same location. And that caused people to sort of rethink a couple of assumptions. And it turns out that when you're dealing with AI, particularly with, say, the LLMs, large language models that are in particular vogue right now, right? There are two distinct operations. There's training a model, and there's using a model, running inferences against a model. Model training really does require huge banks of dedicated GPUs. It's just an incredibly resource-intensive process. But once you have the model, and particularly if you've got a well-optimized model, you don't really need that much GPU power. You just need to make sure the GPUs are close enough in proximity to the users you're trying to reach, so that you can, minimize the amount of time spent inferencing and minimize the network latency of that as well. And that's where I think edge on AI is starting to emerge as a real strength, right? In that you can just install a couple of GPUs in some of these nodes that are much closer to the end user, and then be able to push the inferencing operations out of the big data center on the coast and toward the end user, so that you're going to get better performance. You're actually going to get better data sovereignty, localization, all the things that an AI actually benefits very much from being able to know where a user is, because then you can kind of engineer the prompt to say, this is relevant to Matt in Colorado. This may not be useful to somebody in Boston or somebody in the Pacific Ocean on an island or something like that. And so that kind of thing can really, even sort of behind the scenes, augment the quality and the integrity of the data that an LLM will be able to generate, or another kind of AI model. So it's a very exciting time to see that breakdown in tasks between training and inferencing lead to this sort of new topography of how we can build, new topology of how we can build AI-enabled applications and push them closer and closer to the user.
I see that as very much obviously an evolution. Like when you look at your AI deployments, you can use CPUs, GPUs, and whatever other technologies, if you want to go with TPUs and other for certain vendors and such. That definitely is, kind of a go as you grow or grow as you go kind of a model. I think it kind of ties back to, our earlier discussion when we look at serverless and serverless for WASM. It tells me that, when you look at after you've trained these models, is WASM and serverless kind of the next kind of approach to this? Are we looking at utilizing serverless technologies for WASM, and the trends for serverless WASM, will they continue to rise, or will they change?
And I think the kind of neat thing about a binary neutral format like WebAssembly is that when you're dealing with AI inferencing or things that typically are very hardware bound, having that layer of abstraction, that means the developer can write code that's going to work and run anywhere, can be really, really powerful and have a very profound influence on our ability to sort of spread this technology out on toward the edge, which again means getting closer to end users, meeting those end user expectations performance-wise, and being able to sort of reap the benefits of better localization and drawing from more immediate data sources. So I do think that there's a lot of potential here over time for WebAssembly and AI to sort of emerge as the power couple of this current wave of computing technology. I think we will continue to see some evolutions. On the AI side, efficiency is becoming a big deal, and we are starting to see AI model providers starting to say, how can we really optimize the inferencing speed on this? How can we optimize for smaller sizes? And there's going to be a sort of a race to see who can get the fastest on that side. That only helps this story, right? And the more we can lower resources, more we can lower the cost of egress fees, the more we can lower the cost of running those heavy duty compute workloads, the more money we save while providing the end user with the best experience. So I'm excited about that. I think WebAssembly 2 is going to continue to evolve. Even a week ago now, the Oracle team started talking about Java on WebAssembly. Java was sort of the last big language that needed WebAssembly support. When you see that, I mean, when I think of the number of heritage applications written in .NET and Java, we got Rust and Go and all these trendy languages, but .NET and Java, if we see WebAssembly meet those environments, those ecosystems, and support those, that's going to be the tipping point for WebAssembly. And you will start to see very massive adoption of that in classic enterprise architectures that have been bound by sort of heritage applications that they don't want to rewrite into a completely different language just to get, this kind of benefit. So it's a very exciting time right now.
I agree. And this is something that I've been touting for a while. And I was saying, 2024 was the year of WASM because of the adoption of using .NET and bringing .NET into the fold, and now Java. This is definitely where it's going. Matt, there's a lot here that, I think from a maturity perspective, Organizations are thinking about this. They don't know how to deal with this. But it's just really new to a lot of organizations. What do you think? I mean, we threw a lot out in this conversation about how we can optimize the cloud native approach and edge approach, as well as using WebAssembly and WASM. What do you think? Where can we steer the audience to learn more about this technology?
Yeah, and in the last couple of weeks, and even as recently as yesterday, we had some big announcements come out about this. At Google Cloud Next, we've been talking in conjunction with the Google team about achieving some really profound benchmarks because of Google's new auto-scaling technology applied to a WebAssembly runtime, notably Fermyon platform. So it's great write-up on that just came out. A week ago at KubeCon, we made a big announcement with Akamai, about deploying WebAssembly applications into Akamai's network. And again, Akamai is the biggest edge network in the world. And to be able to reach out to Akamai's absolutely vast network and be able to provide your end users with this sort of like blazing fast WASM performance tied to this, lowest latency in the world network performance, it really tells a profound story. They too have begun rolling out GPUs. And so we can do AI inferencing now at the edge in some of these like very extreme cases. Really, really exciting stuff. So yeah, we'll drop a note in the show notes to that particular release too. And then at KubeCon 2, the Spin and SpinCube, the sort of developer tool and runtime tool for writing and deploying serverless functions that are built in WebAssembly, both now are under CNCF, the Cloud Native Computing Foundation, same organization that manages Kubernetes and many of these other sort of core cloud native technologies, is now sort of spreading into this edge native sector, and it's very exciting.
Matt, I want to congratulate you on your growth and the success. I mean, these announcements are really powerful. Working with these vendors in the market, they're really industry movers. It's really going to help accelerate the adoption of WASM and WebAssembly overall. Get the message out there. Let organizations know they have choices, they have alternatives, they can produce and deliver, addressing those things like skill gap issues and operational efficiency. So I definitely think that that's a big plus here. I want to thank you for your time and your insights. It's really been great. It's always great talking to you. Seeing you at the last events and such has been awesome. The last couple of weeks. But I also want to thank the audience for watching. There's a lot here to unpack, a lot to think about. If you're new to this, there's a lot of resources available. If you're not new to this, this is old hat for you. There's so much more coming. So we definitely want to keep the conversation alive and growing. Reach out to Matt or myself on social channels, and we'll continue that conversation. So thank you very much, and thanks for your time.
Yeah, thank you all.